Welcome back, lecture 5.3, where now we're going to take what we've learned and apply it to 3 dimensions. So 3-dimensional materials. All right, so last time we talked about the 1-dimensional isothermal compressibility and the 1-dimensional coefficient of thermal expansion, right? Alpha and the Young's modulus. So now we're going to extend it to 3 dimensions, right? And what I'm going to do is just sort of tell you the coefficient of thermal expansion in 3 dimensions is called beta. Okay, so beta is defined to be how the volume changes with temperature at fixed pressure. Okay, so this is partial V partial T, so how the volume changes with temperature, so the coefficient of thermal expansion. Normalized out the volume dependence, right? So that's why this 1 over V, and we need at a constant pressure. For 1 dimensions, we thought about constant force, but here the 3-dimensional analog of force is pressure. Okay, so this will depend on temperature, right? And so we'll have to define it where it is, approximately what temperature. So just for scale, so copper, beta is 5 times 10 to the minus 5. And what should our units be? Well, volume divides out volume, so our units are inverse Kelvin. So glass, beta is 3 times 10 to the minus 5, inverse Kelvin. And mercury is 1.8 times 10 to the minus 4, inverse Kelvin. Okay, so what does this tell us, right? So one thing, beta can be defined for a liquid, right? Here mercury is a liquid, these are solids. So our alpha, our coefficient of thermal expansion, could only be defined for a solid, right? Here, beta can be defined for a liquid or a solid because we're dealing with volumes and pressures. Great. So that's one thing it tells us. So another is that we can actually glean information from this. So let's think back to our example of our thermometer. So let's make a thermometer with a bulb of mercury, right? So the mercury has some level which goes into the bulb. And this is actually glass, right? So we have a glass bulb filled with mercury, and this is our kind of our thermometer, right? You put it in your mouth and you see how much it expands, right? So here you can see that not only is our glass changing, not only is our mercury changing, but so is our glass, right? So if we want to know how much the volume changes, just delta V over V, right? So delta V over V is going to be beta delta T, right? So this is our proper form of it, but if we're just going to look at some small region, we can just look in some linear region, right? So that is if T goes to T plus delta T, and V goes to V plus delta V, right? Then what is the beta can tell us how much things change. All right, so let's look at the comparisons. So beta for mercury is approximately 6 times the beta for glass. So that means the mercury in this is expanding more than the glass, but not lots and lots and lots and lots more, right? We can actually even calculate, for example, if we go from 0 degrees from 0C to 100C, let's say the working range of this thermometer, how much does the volume change of mercury? Well, you can just calculate delta V over V. So this would be a percentage. So mercury is 1.8 times 10 to the minus 4. Units are inverse Kelvin. So we need to take our delta T, which I've defined in Celsius, and convert it to a Kelvin. That's easy enough. That's 100. Right? And so this is 1.8 times 10 to the minus 2. Or another way to say it is 1.8%. So it's actually a relatively small percentage change that's happening in our thermometer. So we can imagine heating up, but it only heats up, it only changes its volume by 1.8%. And really what that is that's the geometry here. You have a big reservoir, so you can have a considerable volume, right? And then you have this very thin tube. And so the thinner it is, the volume changes, the area is very small, and so the height change is large, right? So if this area, you want to keep the area small, right there, so that the height change could be large. So in some ways, it's a geometric amplifier of this volume change. Okay, so that's our coefficient of thermal expansion. I'm going to stop here, and we'll go on to the three-dimensional analog of our Young's modulus.